It's Paul here, and I'm going to show you how to use R to calculate the determinant of a 3 by 3 matrix by the three techniques mentioned in the Hubbard's textbook. One of these will work for an n by n matrix. For the others, it's a challenge for you on the workshop problems or the homework to extend it, at least to the 4 by 4 case. So let's start with the sum over permutations. It took me a while to find how to generate all the permutations of a vector in R. It's hidden in a library called combinate. And if you run this script, you want to remove the comment here, run install packages once and only once. It takes a little while. You'll get a message that the package has been loaded, and then when you call the library function, the function you need will be available. I'm going to do the 3 by 3 matrix that's in the lecture notes, call that little m, and let's try generating all the permutations of the columns. I do this by calling the function permn in the library we just loaded for the vector 1 through 3, and if you look at these, you'll see they're generated in a rather interesting way, which I replicated in the lecture notes. You start with 1, 2, 3, then you swap the second and third elements to get 1, 3, 2, then you swap the first and second to get 3, 1, 2, then you swap the second and third again to get 3, 2, 1, you swap the first and second again to get 3, 2, 1, and finally you swap the second and third again to get 1, 3. So every time you're doing a single swap which changes the sign of the permutation. That means these permutations are successively even, odd, even, odd, even, odd, and I'm going to take advantage of that fact. The first permutation is even, so I want a plus sign, but it's convenient to raise -1 to the first power, so I'll slap an extra minus sign in front to get a plus sign. And then what I need to do is take, as the Hubbard's formula shows, the entry whose row is 1 and whose column is sigma of 1, multiplied by the entry in row 2, for which the column is sigma of 2, multiplied by the entry in row 3, for which the column is sigma of 3, and I get the first sum in the term. The next permutation is odd. I can take that into account by using minus the quantity -1 squared times this product of 3 entries. And if I run through all of these, I will generate the 6 terms in the sum over permutations. Now we want to sum them up. Now the following code only works in the 3 by 3 case. It's pretty obvious how to extend it to 4 by 4. A little less obvious to extend it to n by n, but you're not being asked to do that. I'll use a variable called dt to hold the sum of the contributions from the 6 permutations, and I'm running through the length of this list of permutations, all p, and for each permutation what I do is select the ith entry from the list. Since it's a list, I need not single square brackets but double square brackets in order to extract the ith element, and then I just add on to dt -1 to the I. That gives the correct sign depending on whether the permutation is even or odd, times the product of 3 entries, 1 from each row, selected in accordance with the permutation we're using, and the answer comes out to 2, which is correct. Now let's try column reduction. There's our good old matrix M. I'm going to assign 1 to a variable called determ, which at the end of the process will hold the value of the determinant. In row reduction, we were striving to get pivotal columns. In column reduction, we're striving to get pivotal rows. Fortunately, we have a pivotal 1 at the left-hand end of the first row, and what we have to do is clear the other entries in that row. That means we've got to take the second column, subtract the first column from it, and we have to take the third column and subtract the first column from it. And when I do that, I end up with a matrix where the first row is pivotal. Now we want to make the second row pivotal, but unfortunately, our candidate for the pivotal one is sitting over here in the third column. So we have to swap columns 2 and 3. In the process of doing that, we're changing the sign of the determinant of the matrix. So I replace determ by minus determ. And then I swap columns 2 and 3 by storing column 2 in a temporary vector, moving 3 into 2, moving the temporary vector into 3, and as you can see, I have successfully swapped the second and third columns. I want a pivotal 1 in the second row, and in the process of doing that, in the process of dividing by the value of this entry, I will divide the determinant by the corresponding entry, and I multiply determ by that entry. Now I can make the second row pivotal, clean out the 1 over here, and now I'm almost done. I want to make the third row pivotal, and that means I have to divide this 2 by 2. In the process, I will convert the matrix to one whose determinant is 1, and I have to keep track of the divisions I've done by multiplying the variable determ by the element I'm dividing by. At this point, the matrix is triangular. There are 1s on the diagonal. I didn't quite finish the job of making the third row pivotal, but I don't have to. When you have a triangular matrix, the determinant is the product of the entries on the diagonal. So this matrix, like the identity matrix, has a matrix 1. I carefully kept track of all the times when I changed the determinant, and the variable determ now has the correct determinant 2. Now let's try development on the first column. I'm going to start by writing a function that works in the 2 by 2 case. If the length of the first column is 2, I return the value a11, upper left, times a22, lower right, minus the product of the 2 terms on the off diagonal. I always like to check that things like this work when I write them. So there's a 2 by 2 matrix. Its determinant is 2 times 3 minus 1 times 2. It's 4. And my determinant function works in that case. Now let me show you how to get rid of a row from a matrix, because that's the key step in development on the first column. You have to eliminate the row that holds the element in the first column on which you're developing. So here's our matrix M again. M, comma 2 is the second column, and remarkably, I can get rid of that by asking R to give me M minus 1, comma 2. So I started with the vector 1, 1, 2, got rid of the first 1, was left with 1, 2. I was just delighted to discover, I didn't know this about R before, that if I ask for M minus 1, comma minus 1, I get the matrix M with the first row removed and the first column removed. That's exactly what I want for developing on the first column. So what's the first entry when we develop on the first column? It's the 1, 1 entry in M multiplied by the determinant of what's left when we eliminate the first row and the first column. For the second entry, I have an extra minus sign, so I have to take minus 1 times the determinant of the matrix that I get by eliminating the second row and the first column, and the same thing works for the third column. Now I can define a function that works in the n by n case. In the base case, where the matrix is 2 by 2, I return the value I've already found. Otherwise, what I do is initialize a variable to hold the determinant and go down the first column, subtracting minus 1 to the I. That will give me a plus sign for the first entry, a minus sign for the second entry, and so on, times the entry in the first column, times the determinant of what's left when I eliminate the ith row and the first column. And when I try that, I get 2. This, in fact, works for a determinant of any sign, but don't get sucked in by it. This is a terribly inefficient algorithm because it keeps recomputing 2 by 2 determinants over and over again. This, in my opinion, is characteristic of recursive functions. They're easy to write, they're very short, they look very cute, but they frequently do a lot of redundant calculation. So for 4 by 4 or even 5 by 5 on a fast computer, this is okay. But if you really want to calculate determinants of larger matrices, what you want to use is the column reduction technique. And that concludes my little discussion of determinants.